Okay, optical disc fundamentals time. You might already be aware of this, but optical discs are read by shining a laser up at a reflective disc that is covered with little pits. These pits are roughly 1/4 as deep as the wavelength of laser light that will hit them. I ran into some inconsistencies regarding the exact depth of the pits, because the only source I found which specifies it has the wrong wavelength of light listed for the CD, but all you need to know is that when the focused laser hits a pit, the increased depth causes the reflected light to destructively interfere with the projected light, which reduces the overall intensity of the light reflected back. That's actually a pretty neat part that often gets overlooked. Endless articles talk about the fact that the pits change how the light is reflected, but very few mention the destructive interference aspect of it. I've shown this diagram before, and it perfectly demonstrates what happens. When the laser hits a not pit, the light gets reflected right back down to the laser and a prism reflects some of it into the photocell. But when it hits a pit, the destructive interference greatly reduces the intensity of the reflected light, so very little light hits the photocell. An optical disc seemed the perfect format for digital data because you could easily just call a pit a 1 and a land a 0. But that's not how it works. No, the pits and lands are important, but it is the change between a pit and a land that encodes a 1, and no change encodes a 0. This is time-based, so a 4-bit span of time which is comprised of either all pits or all lands will produce 4 0 bits. Start the sequence with a change and then continue as is, and you get 1 0 0 0. No change, change, no change, no change, and you get 0 1 0 0. And you get the idea. This is called non-return to 0 inverted encoding. Now, this has limitations because a long span of zeros requires an outside clock to keep track of how many dead spaces have passed. The longer you have between ones, or changes, the more ambiguous the number of zeros becomes. I know what you're thinking. Was that 6 zeros or only 5? Well, to tell you the truth, in all this excitement, I kinda lost track myself. Which is why you need an outside timing source, keeping track of how many bits have passed. This isn't somewhere you should just feel lucky. But that's not a problem. What is a problem is the nature of everything. How likely do you think it is that a pressed CD is absolutely perfect, has no scratches at all, and that the CD player reading the disc will perfectly, without any errors, reproduce the correct sequence of 1s and 0s? If you answered not likely at all, you're a winner! To help make the data less susceptible to stupid little things, 2 robust error-fighting mechanisms are built into the data stream. The Red Book Standard, the first of the Rainbow Books that defines the physical, digital, and other various standards surrounding each type of compact disc, not only specifies the sample rate and bit depth of the compact disc digital audio format, which as previously discussed is 44.1 kHz 16-bit, but it also defines how the data is encoded on the disc. Now, this is rather technical, but I think interesting, so bear with me. So, each audio sample is a signed, which means it can be positive or negative, 16-bit 2's complement, which is a mathematical operation on binary numbers that we're just not going to worry about right now because it hurts my brain, integer. I mean, we know we're dealing with 16-bit audio, so each sample is going to be 16 bits. Now on the disc, 12 samples, 6 each for the left and right channels, are stored together in a frame of 192 bits. That's 24 bytes for those playing along at home. These frames are then encoded using an error correction scheme called CIRC, which stands for Cross-Interleaved Reed-Solomon Coding. In addition to adding 1 data parity byte to every 3 raw data bytes, the effect of CIRC is basically to spread the data out over a longer distance. That's where the interleaving part of the name comes from. By jumbling up multiple frames and adding parity bytes, CIRC can correct up to 3,500 bits of error-filled or even missing data, and can compensate for up to 12,000 bits by masking errors via interpolation. This translates to up to 2.4mm gaps in data being completely corrected for, and up to an 8.5mm scrambling of data, either through a scratch or some other damage, being reasonably interpolated and masked. The end result is that the error is either completely corrected or it's fudged well enough that you won't hear it. In addition to CIRC, the use of 8 to 14 modulation limits the total number of possible combinations of 1s and 0s. EFM translates each 8-bit word into a 14-bit word. These 14-bit words are translated back into their original 8-bit words using a lookup table. The point of doing this is to reduce the possibility of errors. The use of EFM makes it such that binary 1s are always separated by at least 2 zeros, and a maximum of 10 zeros. This means that every pit and land is at least 3 clock cycles long. It also means that if the CD player reads 101, it knows it must have made an error because That's not a possible sequence. Plus, with a maximum of 10 zeros, it reduces the accuracy required in the clock of the CD player for worst-case clock recovery, as there must be a 1 after every 11th bit, and this will in effect synchronize and restart the zero-counting clock. Keep in mind that with simple 8-bit recording, you could in theory have 14 zeros in a row. When you realize all of the processing that has to be done by the CD player before it can even extract the data it needs to send to the DAC and play the dang music, you gain a newfound respect for its achievements of the time. Granted, using a lookup table and performing some basic arithmetic is easy for a computer, but the fact that this was being done at a consumer hardware level in 1982 with a data throughput faster than what any contemporary microcomputer would reasonably expect it to process impresses me. Okay, so let's look a little bit closer at the disc itself. First, I want to see if you can spot a big difference between a Laserdisc and a CD. Looking at the edge of a Laserdisc, can you see that seam in the middle? Laserdiscs are obviously double-sided, so that seam is the join between the two halves of the disc, and the data is sandwiched between two sides. But if you look at the CD, there is no seam. One of the weirder things about the CD is that the data layer is actually at the top of the disc, just beneath the label. I've linked to a How It's Made episode on the compact disc that does a pretty good job of demonstrating how mass-produced discs are made. Their manufacture is surprisingly similar to that of conventional vinyl records, as they are stamped, or rather molded, from a master disc. The video does a great job of showing this process, but it skips over the actual etching of the data onto the glass master. In short, the master is covered in a solution that will either evaporate or harden when exposed to laser light, depending on the mastering process used. By using the laser to etch pits into the coating, which is then hardened with the development process, the glass master is now covered in bumps that will represent the lands in the molded discs. The master disc is metallized to harden these bumps, and now polycarbonate discs are molded from it. And that's something that I find really neat about the compact disc. The data in stamped discs is actually in the plastic itself. When the disc comes out of the mold, it's completely transparent, but it has all of the data on its surface. To make the disc readable, it's then covered in a thin film of aluminum via a vapor metallization process, and now the disc could theoretically be read by a CD player. But remember, those pits and lands are on the top of the disc, exposed. If they could be touched, the data would be destroyed. So before the disc can be handled, it needs a thin coat of varnish to be spread along the top, and now the data is protected from damage. Putting the data layer on the top of the disc meant that the disc was even more tolerant of scratches, as these scratches are out of focus to the laser reading the disc from below. This was a pretty smart move. The laser would read through almost the entire 1.2mm thickness of the CD. If you look at a blank CD-R, odds are you'll find these two numbers, 80 minutes of audio and 700 megabytes of data. You may be surprised to learn that these two numbers don't match. See, let's take the 80-minute figure. We know that the compact disc digital audio standard consists of two 16-bit streams, two because it's stereo audio, each consisting of 44,100 samples per second. Let's make it a bit easier and say that it's one stream of 8-bit words, or bytes. So by doubling 44,100 twice, once for stereo, once again to turn 16 bits into 8, we find that it's 176,400 bytes per second. Multiply that figure by 60 for 60 seconds per minute, and again by 80 for our 80-minute runtime, and you get 846,720,000 bytes. It would seem that an audio CD holds over 146 more megabytes than a data CD. What gives? Well, it's actually more of a what takes away, as the CD-ROM standard sacrifices those bytes for more precise error correction. As discussed in the channel's first video on the compact disc, the circ error correction used in the compact disc digital audio standard can perfectly correct errors up to 3,500 bits long. But it can also mask errors up to 12,000 bits long through interpolation. That means that it's essentially guessing what the audio samples should be for errors between 3,500 bits and 12,000 bits. Now for audio samples, that's fine. 12,000 bits is less than 1/100th of a second of audio. So even though the error correction might be fudging things, you'll almost certainly not notice it. But for data, that's not going to do it. Data cannot be fudged without serious consequences. In order for the compact disc to store data files reliably, it would either need to sacrifice durability or come up with a new error correction scheme. And it did neither, but also yes, CD-ROMs, or would that be CD's ROM? used the same circ error correction and basic data structure of the CD audio disc, including the frame structure subcode and all that. But more error correction was added within the frame, which we've now formally decided to call a sector. Of the 2,352 bytes available in a sector on an audio CD, 304 get sacrificed, mostly for error correction, but also for some basic signaling such as synchronization and distinguishing between Mode 1 and Mode 2. Combined with an additional layer of circ error correction, the CD-ROM standard maintained the same durability with zero-tolerance error correction. We'll get to Mode 2 later, but nearly all CD data applications use Mode 1 for its complete error correction. Now that the compact disc was being used for more than a simple linear stream of audio, a true file system needed to be standardized. Initially things were rather ad hoc, but a group of 12 computer hardware manufacturers met at what was then the High Sierra Hotel and Casino in Lake Tahoe, California, where they settled on a standard called the High Sierra format. Eventually, this would become ISO 9660, the standard used to this day. However, it has been extended and improved over the years. Now that the CD-ROM was officially a thing, whole new multimedia experiences could be created. With the ability to store images, program files, sounds, and even video, the possibilities with CD-ROM were seemingly limitless. No longer bound by the 1.44 megabytes of a 3.5-inch floppy, elaborate games with full-on soundtracks, thousands of color images, and more complicated structure could be produced. My greatest nostalgia factor comes from mid-90s educational games like the Magic School Bus games or my personal favorite, Jumpstart 3rd Grade. But unless you're either very young or were living under a rock through the 1990s and early 2000s, I'm sure you already knew what CD-ROMs could do. But the in that CD-ROM, man, that's a bummer. Sure, having 700 megabytes at your disposal is fantastic, but no one has a CD manufacturing and duplication facility just at home. But wait, they do! The development of the CD-R for compact disc recordable meant that no longer would you be forced to write up a contract with a commercial CD pressing facility for at least 10,000 discs just to make a mixtape. Instead, all you needed was a $35,000 machine and a computer. It would take until the mid to late 90s for CD burners to come down in price, and even then there were annoyances, but now we're really talking. A CD-R, which incidentally is a pirate's favorite kind of CD, is constructed much the same as a normal CD, but with two important changes. First, the pits and lands molded into the polycarbonate layer are replaced with a continuous spiral pre-groove. This spiral will guide the laser of a drive writing to a disc, and it also contains the A-tip, which tells the drive the properties of the disc, such as its maximum write speed. Right on top of the pre-groove is a thin layer of an organic dye. That's why CD-Rs are sometimes a strange color or even just a little bit off from the normal silver. Then on top of the dye, a partially transparent thin layer of metal, usually aluminum, is placed. This allows the laser light to be reflected back while still being influenced by the dye. To burn data on the disc, the laser switches from its everyday gentle glow to an all-out light cannon of fire laser, and the high intensity heats up the dye so much that its optical properties change. That's right, CD burners are literally burning the equivalent of pits onto the disc. Once it's been written, almost any CD drive going back to the earliest CD players can read these discs. The parts of the dye that were made into a pit by the writing laser will dim the reading laser's reflection, which is much the same as how real pits cause destructive interference. So long as the CD reader can tell the difference between a burned spot and an untouched spot, it will read the data just fine. Being able to store data files onto a compact disc at home meant that just one of these guys could replace hundreds of floppy disks. Of course, the central limitation to the CD-R is that it is a write-once, read-many format. In fact, its original name was going to be CD Write-Once, which I really wish had been stuck with because we could have called them CD-Woes. Whoa! But we wouldn't be stuck with write-only for long. Interestingly, the Orange Book detailed a rewritable CD based on magneto-optical technology in 1990, the technology behind the minidisc. This never made it to commercial production, but the CD-Mo would have been the perfect companion to the CD-Woe. Instead, we got the CD-RW in 1997. This is functionally identical to a CD-R, but the organic dye layer is replaced with a silver indium antimoney tellurium alloy, also called by at least one person a Ginspati. This alloy has a unique property which alters its reflectivity based upon phase changes. In an unburned disc, the alloy is in a polycrystalline structure. But when the laser heats it to somewhere in the neighborhood of 500 to 700 degrees C, it melts it. And when it solidifies, it no longer has the same crystalline structure, and thus it reflects light about 15 to 25% less intensely than the crystalline parts. So, spots that are melted by the laser turn into sorta pits, and spots that aren't remain sorta lands. What allows the disk to be rewritten is that when the alloy is heated to around 200 degrees Celsius, it doesn't melt, but any parts that have lost their polycrystalline structure will actually reform. This effectively erases all of the burned pits, and allows the disk to be written again. CDRWs have several severe limitations though. Unlike a CDR, these disks generally cannot be read in standard drives. Because the change in reflectivity between a pit and a land is so slight, a CD reader needs to be much more sensitive to pick up the data. After the introduction of the CDRW, many standard CD readers were made more sensitive to accommodate them, sometimes branded as multi-read. But it certainly wasn't universal. Another big problem of the CDRW was that the disks weren't always backwards compatible. Because of that phase-changing alloy, there is actually a minimum speed to write the disk. This basic 1 to 4x disk will work in pretty much any drive so long as you can force it to burn slowly, but later, higher speed disks might need a minimum speed of 8x or more, so if you only had a 4x drive, you're SOL. And finally, one thing you should know about pretty much all writable optical media. The dyes and alloys aren't terribly stable. Many of the earliest CDRs are failing, as the dye is degrading or the disk is delaminating. If you have any precious data stored on optical media, you might want to back that up pretty soon.